If you were sitting with someone who had a red piece of paper and they crumpled it up and threw it on the table and it looked like this, you could say, or I could say, that reminds me of the head of an elephant. Do you see the trunk, the big head, the ears? But it's not spooky, right? You would think, oh my goodness, how did you make the head of an elephant by crumpling up red paper? Because you have to sort of impose the head of an elephant on that, right? It's not compelling. You can see it when I point it out, but it's not really that remarkable, is it? Whereas, if you see this red piece of paper on a table, you know somebody has done something to that piece of paper. If a 4-year-old who had never experienced origami, had never done anything with origami, never seen an origami crane before, came into a room, there's no one in the room, and they see that on the table, they know, he or she knows that someone did that, right? Someone made that, and they also think, I want to know how to do that, right? That's the way kids think. The number of steps you have to go through to get that crane, and even with these directions, you're probably not going to get it right, okay? The number of steps you have to go through to get an origami crane is too numerous, and each step requires too much precision in order for that to happen by accident. You don't need a calculator in the end, because whether it's 10 octillion or, far beyond that, you don't need the number. It just can't happen. And that's why these things are so obvious. That's why you don't need to be an expert. This is a monster protein RNA complex called the ribosome. This is the molecular machine that builds proteins by reading the genetic instruction on an RNA. And you don't need to worry about all these terms, just look at it, okay? That's more sophisticated than an origami crane. So this is the level that I have been looking at life for many years now, looking at individual protein molecules and asking whether they themselves are too remarkable to be coincidences. Because you have to arrange this machine is reading along an RNA that came off of a DNA gene, and that has sequence instructions, and this is the machine that is reading those instructions and putting amino acids to play, connecting them to form a long chain of amino acids that is sequenced according to the genetic sequence on the gene in order for this long chain to fold up and form one of these, a single protein molecule with these really elegant three-dimensional forms. There's thousands of these forms that have been cataloged now. I'm just showing you a few so you can get an idea of how sort of visually attractive they are, but also how varied they are. They come in all kinds of different shapes, and those shapes are critical for what they do. So a lot of these do chemistry. They are molecular machine parts. You saw a diagram of the flagellum. All of those pieces of flagellum are protein chains that fold up to the right form to make that flagellar motor. And the question that I was asking when I embarked on this at the protein level was, how fussy is the order of these amino acids in this chain in order for it to form a shape that will actually work in a cell? The number, if you want the probability for getting the protein fold, is 1 in 10 to the 77th power. That's 1 in a trillion, 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 trillion. A little bit worse than that, but I got tired of saying trillions. So it's like having laser points, laser dots the size of hydrogen atoms. That's a very small laser dot. And the ceiling would be the size of the backdrop of the visible universe. Okay? All right? Think about that. One dot, hydrogen atom, hidden at the backdrop of the visible universe, and something blindly searching that huge shell, hoping that these two hydrogen atoms, oh, you were close. You were so close. But it's just not going to happen. Obviously not going to happen.